Thank you all for coming. In the year 2008, other than the subprime financial crisis, something amazing happened. 23 of the 24 world records in swimming during the Olympics were broken wearing the same swimsuit, Speedo, LZR. It was developed by taking the top swimmers in the world, flowing water through them, detecting micro turbulences from the skin, and then modeling a swimsuit to reduce those turbulences. And you can see the material being developed here. Silvery parts are hard, that shapes the body, and then the dark parts are shark skin-like to prevent the microturbulence. It is so good that the teams that did not wear this swimsuit complained that this is technological doping. Yes, but FINA allowed it. Yeah? And you can see. Now, it is so good that Nike sponsored swimmers. Nike, went to Nike and say, please let me wear Speedo. Nike, for patriotic reason, said, okay. So this is the world record, 4x100 freestyle men wearing this swimsuit. Record for 11 years, not broken. You know why? After the Olympics, FINA banned the swimsuit. I show this example to let you know the technological edge that is being given. 11 years edge, still not broken today. No record has stood so long. Yeah. Just out of interest, maybe Mikhail, you give a small prize. There are 2 Nike-sponsored swimmers in this team and 2 Speedo-sponsored swimmers. Who can spot who are the 2 Nike-sponsored swimmers? Raise your hands. Mikhail will give you a prize. Yeah? Yes. Phelps, Speedo-sponsored swimmer. Speedo logo. Jones, Nike-sponsored swimmer. No Speedo logo. Nike said, you wear Speedo, take out the logo. Weber Gale, Speedo logo. Lizak, no Speedo logo. If you got it, Mikhail, the gentleman here, right? Okay. This swimsuit was modeled using a set of rules, mostly fluid dynamic rules. Rules are important. Rules were developed by humans, a lot of them represented as equations. Another example. This is a human heart, modeled at very high detail at Stanford University, using 3 sets of rules. The first set represents the mechanical pumping of the heart, so a set of equations for that. The second set of equations represents the electrical activity that excites the heart. The third set of equations and rules represents fluid flow of the blood through the heart. 3 sets. The reason they model this heart accurately is because, for example, they would like to be able to help doctors, surgeons, insert pacemaker accurately into the heart and run this model with these 3 sets of rules to see if the blood is still flowing correctly. One of the reasons they do this is because these wires break. There was a 2-year-old girl had a heart defect that had to be inserted with this wire. And by the time she from 2 years old to 20 years old, this wire broke 4 times, and she had to be operated on 4 times. So insertion of this wire is very important. So this model is used for such kind of insertion. You know that heart band, you can see, that heart band there is very likely where it will break. Yeah? 3 sets of rules. If I see a few hands, I will show you. Anyone interested, just to get an idea, what is the fluid flow set of rules look like? Okay, here it goes. Don't worry, right? Yeah, here it goes. Don't worry. This is the Navier-Stokes equation. Basically, this represents how hard the heart pumps. This represents how thick your blood is. Blood thicker than water, thinner than honey. Yeah? This represents your blood pressure. The three combined in the dynamic way will then figure out how the blood will flow through the heart. Yeah? Set of rules. For those interested, this is called the Navier-Stokes equation. You study it when you go do mechanical engineering. MIT is great for this. Yeah, right? Okay. Basically, you put those rules into the model, those rules over there. You put in the current condition, you hope to predict the future. The future could be 1 second from now, 1 month from now, 1 year from now, 100 years from now, depending on what sort of rules you use. Do they use such rules in Wall Street for financial trading, for stock trading? They do. I went there. Actually, those rules are quite simple. You take, if the 50-day short-term moving average of the stock cuts over the 200-day long-term average of the stock, automatically buy. Don't even talk to a human. Yeah, of course, every trader will have their own secret sauce. You have to say, if it is a Monday and if it's raining, don't buy, right? So you got all sort of rules that humans give to the machine. And then the machine just follow the rules and predict. Five years ago, something changed. I went back to Wall Street, and then they were starting to set up a separate department, very young engineers, not physicists, like on this side here, but data scientists that don't care about rules, don't want to know, right? It's totally isolated department, not talking to the rules people. They don't want to know, right? Yeah. All they are interested in is your history. Those young chaps, young ladies, just came in to the department and just asked for all your historical archive data. That's all they're interested in. Don't tell me about rules. I don't want to know. It will influence me. I just want to look at your data. Yeah? And then they will feed that data into their model. And then as they feed, the model slowly evolve to be able to predict the future. Oh, I said, how do you write such a program, huh? A very smart one, is it? No, actually quite simple. You just give the program a set of adjustable dials or knobs, right? All set to neutral. Feed in the first example, predict wrong, adjust the knob. Second example, feed in, predict wrong, adjust the dials. 1,000 examples later, trial and error, adjust the dials, adjust the dials, adjust the dials. 10,000 examples, 100,000 examples, 1,000,000 examples later, the dials get adjusted to a pretty good place to make a prediction. This is machine learning from data. This is how machine learns. It's just lots of trial and error. But you need lots of good data to trial and error with. I did not believe, okay? So I did not believe. I knew the method, but I did not believe that it can be so accurate. So I went back to my lab. I got my intern to try this out. I say, predict for me whether it will rain tomorrow at San Francisco airport. But no rules, huh? Don't talk to meteorologists. Don't read any weather textbook. Just use the 40 years of weather report data from NOAA. What she did, she set all the dials to neutral, and 40 years is 15,000 days. She took the first day, feed in, predict, rain, no rain, wrong, adjust the dial. Second day, wrong, adjust the dial. 10 days, 100 days, 1,000 days, 10,000 days. 15,000 days later, this is the dial adjustment for whether it rains tomorrow at San Francisco airport. No knowledge of weather forecasting, just data. You don't even need to know what all these means. You just treat them as parameters. Of course, I'm simplifying it, right? So I asked her, how accurate is this recipe of dials for predicting whether it will rain tomorrow at San Francisco airport? weather forecasters went to grad school with a PhD, came back and predict weather at 95% accurate. You don't even know what weather forecasting is. You just use data. How good is your prediction? Her prediction was 85%. Not as good as going to grad school, but she has no knowledge and able to get 85%. Very good. This was a learning process. Of course, I had to check the answer, right? I asked her, if I predict no rain all the time, how accurate am I? 75%. So, for those who know data, this is the obvious question to ask. Yeah? So her 85 is better than the 75. Yeah, naive answer. This is machine learning. The world is developing to be two kinds of prediction. This has always been the traditional, and it will still stay the gold standard, because in there are all the rules that human history has developed. A lot of Nobel Prize-winning equations, like the Black-Scholes for predicting derivatives in markets, like the Navier-Stokes equation for predicting fluid flow, all sorts of equations winning Nobel Prizes plugged in. And they predict the future very, very well. But they are only as good as the right equations you put in by humans. Sometimes you miss some of them. This one doesn't care about rules, just cares about your history, your historical data. Not as accurate as this, but it gives you a new perspective on things. These will be the two new ways. This will be the additional way of making predictions going forward into the future. Have to accept it, because the machine has got fast enough, data has got abundant enough, and access to that data has got easy enough to do this. Yeah. Just to close on this introductory session, the dials I showed you are 1, 2, 3, 4, 5 here. The weather example was 10. How many dials for an autonomous car? 1 billion. That one you need data scientists, yeah? Okay? And how do you arrange those dials? In a network. Every line is a dial. The dial just says, is the line important to pass that data through, or line not important to pass that data through? So some lines will end up thicker, some lines will end up thinner, and some lines will go away. That's a neural network. So a machine learns from adjusting dials to be artificially intelligent. That is the introduction of machine learning towards AI. So the world got together and say, as an example, let's all compete to see how well this thing does. This dial adjustment, right, with data. So they collected 14 million images from the internet, right? And then say, all of you welcome. Compete who can recognize objects in those 14 million images best. How many mistakes you make. The teams that came in 2010, 2011, long ago, right, were making 25% error in recognizing things in the 14 million images. While we humans, B stands for brain, were only making 5% error. I don't know, poor guy, whether he or she looked through 14 million images, I don't know. Maybe a sample, huh? Right? Those rules-based systems, these were rules-based systems, not machine learning-based systems. Rules-based systems. They were making lots of error. They were recognizing paintbrushes very well here, but not there. Confused. Right? How many more rules do you have to write to try and recognize a paintbrush in those scenarios? They could recognize sunflowers very well here, but they will go confused there. You see the problem with rules, right? For this kind of situation, how many more rules do you have to write to anticipate all the different kinds of scenarios? So the teams got together and say, I'm going to use instead the machine learning way and use the 14 million images as examples to train with. Very smart. Since I have the question, why don't I use the question to train on? Because I also have the answers. So they use the machine learning way with dials, right, in the neural network. And the very first team that using deep learning, which is the machine learning way, with many layers, improved to 15%. Oh, they say this is a good advance, big jump. And by today, It has improved to 2%, and it is done. Fixed categories of recognition of images better than humans by far. It is done. At least this particular way of prediction. However, do note, 2% error is not 0% error, right? So if you put this in an autonomous car, don't expect it to be perfect. Yeah. So these things are not perfect. Most of the time, they are mainly better than humans only. Something to keep in mind. We also have a customer with 2,000 retail stores. They would like to be able to recognize their VIP that opt in within 5 seconds so that the store manager will rush to the VIP customer, shake the hand, and provide a concierge service. This VIP can be recognized at any of the 2,000 stores without even needing to know his or her name. Lesson learned here. Our proof of concept worked for 100 cameras, but then when they deploy 50,000 cameras, it requires a different infrastructure. So one thing to remember, when you go from proof of concept to production, remember about scalability. We were called to a hospital with high incidences of tuberculosis in the city. The city decided to x-ray everybody above a certain age. Everybody come in and x-ray. The x-ray machines were fast enough, but the problem was the doctor's diagnosis backlogged 2 weeks. The problem is, if someone is infected, after an x-ray, he or she continues spreading the disease for 2 weeks before the doctor calls him or her. Problem. So we went in there and took all the x-ray images of history that were already well labeled with TB, without TB, by doctors, and train it with our neural network. This x-ray image, no TB. This x-ray image, no TB. This x-ray image with TB, and so on and so on. After training it with about 50,000 images, we plugged this predictor right next to the x-ray machine, and now a new patient comes in after an x-ray. Within 1 second, the machine say, "You are okay." Oh, by the way, you still have to wait 2 weeks for the doctor to certify you okay. Yeah? But so far, I've not been wrong, right? I've just dramatized it, but you get the idea. More importantly, if after an x-ray in the machine say, "You are not okay," the doctor rush in and stop you spreading the disease right there. Very profound. Very simple, straightforward application, but very profound implication. Lesson learned here. Don't try to make the machine do too many things. Be more specific, more specific, more specific. It can predict better and sustain the prediction. By more specific, I mean, in this case, only X-ray, no MRI, no CT. Only chest, no head, abdomen, or legs. Only TB, no pneumonia or anything else. Just make it specific, and it will be good and stable. Formula One fans here? Ah, great. Okay, good choice, Mikhail. Thanks for suggesting I take this example. Later, you'll see more details from a presentation on it. We were asked last year to help design the Mercedes Formula One car using machine learning. Can't say much more. Did not sleep in January well for 3 nights during the first Grand Prix, because if they don't win, I'm maybe not here today. Right. Okay. Right. After 16 races, they won 11. Not too bad. And then 7 of which are first and second. Yeah. I just touched some insulator. Right. All right. So far, so good. So I'm still here today. Right. I can't say much more, but how do I convince you that we work closely with them? If I took a picture with Hamilton, not convincing because many people have taken pictures with him. So I took a picture next to his car behind the red line while they're assembling it before he goes out on the race. And they didn't kick me out of the place. Yeah. All right. All right. Sorry? Yes, Photoshop, yeah. Yeah, it's real. All right. Okay. Later you'll hear a bit more about, a little bit more about what we do. Lesson learned here. We developed a technique that accelerated the design of the car from 3 weeks down to 1 day. Fantastic. I went back 3 months later and asked them, did it improve from 3 weeks to 1 day? Oh no, it improved from 3 weeks to 1 week. Huh? Oh, but I'm already very happy because it's 3 times the performance. But why still 1 week? It should only be 1 day. Oh, they say, then what do you do with the 6 days? Oh, I spend the 6 days checking the answer of the machine. Trust. Expect that you or your customers or your employees or your management will not trust the machine at the beginning. So set aside time and expectation for gaining trust. Now, eventually they switched to 1 day, but it took them 3 months to trust it enough to switch to 1 day. Same with the X-ray, right? The machine says you are okay, but qualify by saying that you still need a doctor to certify you okay. But on the side, you say, I've not been wrong so far, right? Remember, set aside time for trust, to trust the machine. We also send a server to the space station. As Mikhail said, we are data-driven and edge-centric, cloud-enabled. Edge-centric, right? Who has the furthest out edge? Must be HPE, I hope, yeah. So we plugged, the SpaceX was plugged into the dotted line, and you will see the astronaut bringing into the hard line. This is astronaut Mark van der Hey, and the date is September 14, 2017. He's bringing 2 HPE servers that we just took straight off the shelf before launch. That's the key part. No hardening by hardware. We just open up the price book, the very latest 1U server, ship it to NASA, put it in a locker, and go to space. Yeah. Where the hand is put up there is where Mark van der Hey will plug the server. Oh, we spent 6 months making sure nothing complicated went wrong, and we forgot the cables were too short. Yeah. Yeah. Lesson learned here, right? Sometimes the simple things get you, right? Yeah. Don't just concentrate on the complicated thing. Yeah. So we needed a second astronaut to help you, just to convince you, right? You can see the HPE logo here. It's up there. Right? Almost didn't happen with the logo. Any interest in the story behind this logo? Oh, okay, right. It was originally an SGI logo, Silicon Graphics logo. I tell you the story. Because it was before HPE acquired SGI, so we were going to launch with the SGI logo. And then when we shipped the machine to Houston to get ready for launch, test and ready for launch, I heard that HPE was acquiring SGI. I called up my engineer, drive down to Houston with a screwdriver, yanked out the SGI logo, and super glued the HPE one in there. Now you know the story. That's why I can use this video right now, else I can't, right? Yeah. Oh, and 1.5 years later, astronaut Christina Cook de-installed it. I was very glad. A male astronaut installed it, and a female astronaut de-installed it. Yeah, good balance. Yeah. Yes. Yeah. Beautiful. So you spent 1.5 years at the space station running application non-stop and did not break. And then you returned to Earth on June 3rd in SpaceX 17, and it went through the very harsh condition of the atmosphere to arrive at 300 miles off the coast of California. And you can see how tough the condition is on the capsule. We call it affectionately the toasted marshmallow. Yeah. Yeah, our server was inside there. We took it out, sent it to our lab, rebooted it, it worked. Yeah, goes to show the stability and robustness of the system we built. It was just straight off the price book. We won the NASA Exceptional Technology Medal just a few weeks ago for this work and the lessons learned from this experiment. Yeah. Okay. All these examples I've shown you were based on machine learning from examples, past history examples. And their goal was to predict a future that is fixed. You just don't know what it is, you just have to predict it. In these next examples, something different. The future is constantly changing. because you have an adversary, an opponent that's constantly changing strategy. That's why we use games to test whether your machine is good at not its passive prediction, but a constantly dynamic one. So we use games. IBM beat the world top chess player, full respect to them, in '97. Fewer people know that University of Alberta beat the world top checker player 2 years before that. Full respect to Google for beating the one of the world top Go player. Go is the toughest game there is. 10 to the power 171 combination is a crazy big number, right? If you took all the computers in the world combined, Facebook, Google, everybody, run for 100 years, you only do 10 to the power 30, not 171. So we do not solve Go. We only got machine to play Go better than humans. Remember that, yeah? Remember the example of imaging? Better than humans, not solve Go. We are far from solving Go. We just managed to get the machine to learn from data to be better than humans. Yeah. What do I do here? I'm the CTO for AI at HPE. What do I pick? I have a problem. Yeah? There's no game tougher than Go. I picked poker. Yeah. A bit controversial when I picked it, yeah, but I had to explain why. Poker might not be as many combinations as Go, but it's already a crazy big number. This is Texas Hold'em, heads up, no limit, for those who play poker. Anyone? Yeah, okay. Well, we have to be careful then, huh? Right. There's one thing different with poker against all the others, and that is, all the others, you know your opponent's pieces is clearly in front of you. In poker, your opponent's pieces are hidden from you. Not only that, the goal is for the opponent to bluff you. So the objective is constantly shifting. And you also don't know all the information about the objective. I like this because it is useful for cyber defense, useful for auctions, useful for business negotiations. Yeah. So we have to then see how we can compete with humans. IBM, rightfully, to compete with humans, went to a formal chess tournament. Google went to a formal Go tournament. Wear suit, sit down nicely. We went to a casino. Yeah. Right. This is Jason Les, one of the world's top Texas Hold'em heads up no limit player. And this is us, innocent looking, yeah, except for this duct tape that goes behind the curtain of a $3 million machine. We still lost. We lost $700,000 in 2015. Yeah, almost didn't stand here today. Yeah, yeah. With Professor Sandholm, who is the PI for developing this code, we asked the 4 top poker players. It competed against 4 players. You can see, right? Asked them, what happened? How do you manage to beat the machine? Because when we observed at the beginning of the tournament, the machine was winning, but near the middle, you started to win big against the machine. What happened? All 4 almost said the same thing. The machine did not bluff very well. Eventually I figured it out. Okay, Sandholm said, give me a machine 10 times faster, and I'm just going to train my machine on nothing but bluffing for 1 year. I dramatized it, but that essentially is it. Basically, he took 2 machines and said, keep playing, even randomly at the beginning, never mind, right? And every time one of them happens to win because of bluffing, give it a reinforcement learning. After 1 trillion games, it should get pretty good. Went back in 2017, beat the 4 top poker players, $1.7 million. Yeah. It has not lost since. We asked the 4 poker players again, so what's different now? Right? We observed that you are winning at the beginning, but eventually the machine won big. It's a total flip. What happened? You say, oh, the machine bluffed really well now. Right? And has not lost since. The lesson learned here is that a lot of times when you build a machine learning system, because you cannot anticipate all sorts of data you have to feed it, sometimes you need to test it, and if it doesn't do as well, you need to come back and find out what those mistakes are, and you improve it. And you see that quite often. So set expectation that you need to figure out, even after production started, to figure out, give it time to make corrections, because sometimes there are mistakes. Yeah. It doesn't always have to be complex machine learning system. This one is amazing. I was in Copenhagen. One of our customers was collecting data from their supermarkets every night in preparation for machine learning. But before machine learning, they already realized something and came up with this app. This was on a Friday, and there are 36,785 items in the supermarket that they are going to throw away soon because they have reached their sell-by date. They came up with this app so that people can then model their weekend meals based on what's going to be thrown away before the sell-by date. So I just click on my nearest supermarket. I got this list. I managed to buy a bread for 20 cents, a loaf of bread for 20 cents. So this is an example where consumers, responsible consumers, right, try to reduce food waste, right, would be going to the supermarket, deciding what their weekend meals are like based on supermarket perishable goods. Yeah. This is amazing. I checked it on Monday. Right? Oh, by the way, you can see 1.79 krona, Danish krona, 20 cents there, just about. Yeah, I actually ate that bread. Yeah. Save money for the company. Yeah. This was Friday. So Monday, I checked the app. Reduced to 4,000 items. This is amazing. This company is also now thinking, perhaps I do not just a B2C, business to consumer, but a C2C in the future. I think in Scandinavia it works, and that is, me personally, I open the fridge, I realize I'm going on a trip, all these items are going to be wasted. I publish it on the app, and my neighbors come knocking on the door and use the food for me. C2C. This is the future. But it requires a bit more responsibility on everybody's part. Yeah? But reduce food waste can help reduce hunger around the world. Autonomous cars. Oh, the lesson learned here. It doesn't have to always to be complicated machine learning. In order to machine learn, you have to collect data. But sometimes after collecting the data, you can already do good without even starting machine learning. And this good improved the profit margin of this company by 10%. They reduced their waste. And it also helped the earth. And then helped the consumer, triple win. Because you have data. Real-time data. You have to have it every night of all your supermarkets, right? That's the implication. Okay. Autonomous cars. Soon, your cars will be full of sensors. And to use those sensors, the car company will put a 5G cellular chip in your car for free. You don't even need to know about it. And when you approve the sending up of all that data, the company will automatically upload that data into their silos. Soon, every car will have a 5G chip in it and will have about 100 sensors. The problem is, if the car in front is from a different manufacturer from the car behind, what the car in front sees cannot be shared by the car behind today because they are siloed. Different company competing. They don't want to share. So what we do, develop an application for sharing using blockchain with Continental. The car in front, shock absorber, notice that there is oil spill on the road, sends the information up to its own company, manufacturer. The manufacturer sells that information using blockchain without interference by third parties, and then the car behind gets a skid warning and then the payment goes the other way. And then HPE makes a transaction fee. Okay. We have to live. Yeah, we have to live. Yeah. All right. So the goal is, if you send something, you want the car behind, even though of a different manufacturer, to be able to get the information. So the car behind now will see this on the dashboard. When the car in front notices an oil spill, you are about half a kilometer, 500 meters away, say, right? And your dashboard, the car behind, will see two flashing spots on your dashboard, and the flash comes from the car in front of a different make. You would have paid maybe 1 or 2 cents for the information. Collaboration of even siloed data amongst competitors. I think this is profound. Blockchain technology, not blockchain itself, but the technology for blockchain will be the key to making all this successful. Because if you use a credit card transaction for 1 cent every time, a credit card transaction goes through 7 steps before it's done. Right? This one can be done in a very, very few steps and without interference, involvement of any parties, right? Any more parties. So I believe blockchain technology, not blockchain itself, but the technology inherent in blockchain will become more and more important for many of this C to C, B to C, less B to B, but lots of C to C type transaction at very, very low cost. Raise your hands. Mikhail challenged me in explaining blockchain in 1.5 minutes. If I see a few hands, I will spend that 1.5 minutes. Okay, right. Okay. All right. This is a centralized ledger, not blockchain. Normal ledger, the old days ledger, right? John pays Jim $100. Jim went to ATM, withdraw $200. Sarah paid Jim $10, so on and so on and so on. 1 page, 2nd page. And then someone is responsible for this ledger. A company, like a bank, or an accountant. Someone is responsible. Any tampering, the person responsible. All right? Now, a decentralized ledger, like a blockchain, is different. It is as follows. John pays Jim 1 Bitcoin. Jim pays Sarah 2 Bitcoin. And so on, and so on, and so on, and so on. 1 block. Transaction, 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 transaction. Another block. Another block. And then the ring binder is your chain. Also blockchain. Just a different name. Yeah? The problem only you have to solve in this case is that this blockchain now you have to give to everybody. Public, right? The problem with that is what happens if someone tamper with one item here. Well, you use a technique called hash. Very, very important, right? The hashing scheme is where it consumes all the items on your record, consume it, and then it creates a unique number on top. If someone tampers with an item there, that number changes and you will know. And the chain works by making sure as you consume everything on that page, you also consume that number on top of the previous page. And this is how then you figure out if someone tampers at the very last page, you also know right in front, because this number will change. Blockchain. Next time, when someone talks about blockchain, you'll know. It is just another ledger. Yeah? I close this session with this. More and more your employees will be concerned about jobs, right? Why? That's the human brain, us here, and the neural network over there. Do not be concerned because of 2 things. Many things, but I just talk about 2 things today I have time for. 1, the brain, we work with the Blue Brain Project in Geneva, and we know The brain is more than 1,000,000 times more complex than the most and biggest neural network in the world today. So it'll take some time for it to reach there. It will reach there, but even if it reaches there, it doesn't mean a more complex neural network will suddenly get consciousness, right? We don't know whether it will. But still very, very far away, right? Decades, in my opinion. Number 2, do keep in mind that this today is very, very narrow. When it is good, it is very narrow. X-ray only, no MRI, CT. Chest only, no head, right? TB only, no pneumonia. The more narrow it is, the better it is. So it has no judgment, unlike humans. Humans, any decision we make, no choice, we apply judgment. No choice. It's just as professional, we control our emotion when we make decisions. That's all. It's there. Why? Because when we see something at the back, excites our back of our head, it is automatically connected to our logical center. But don't forget, it also automatically connected to our emotional center. And our emotional center is moderated by a logical center. So there is a full connection. So every time we see something to decide, logic and emotion plays a role immediately. Yeah. The only thing is that when you don't get enough sleep, your emotion baseline is higher when you start the day. Yeah. In particular, REM sleep. Yeah. So do keep that in mind. I suspect in the future, as we are relied more and more on making high-level judgment-required decision, we won't be just breathalyzer tests for alcohol. It will be checked whether how much sleep we got the night before. Yes, more and more. Therefore, while the machine is relied on to make more and more of the correct decision for us, we better be here to make sure that they are also the right decision. Because what's correct is not always right socially. That is why we humans still need to be around, at least for a while. Yeah. Okay. But they improve very fast. 3 videos. Right? Here you see a robot moving, right? Oh, not very stable, never mind, right? Oh, I have something to do. Okay, let's pick it up. Yes. Who felt a little bit bad for the robot there? Yeah? Yeah, I didn't show you the rest of the video, right? It was just really harsh on it, right? Yeah. But don't worry. 1 year later, improve. Yeah, no more hockey stick, huh? Right. And 1 year after that, improve some more. Yeah. So these things are improving fast, but we still need to be there to make judgment on the decisions being made by machine. The correct decision is one thing, but we also have to be sure that they are also the right decision. Thank you.